first announcement about the hackathon. So this is the last day of subscription, and the deadline is 6 p.m. So if you didn't find a group yet, please look for it. Some people who, asked for me if they could get a bigger group. For now, we are just asking you to look a little bit more. We've had find some groups who need participants. So, but if you don't get in any option, you will not be unable to participate because of this. We can find a way. Just first, anyone here needs a group yet? Didn't find a group? Please raise your hand. No, you didn't find any group. You are alone, please. If you're alone, you didn't. Just please find higher. You 1, 2, you 3, right? Okay. And who has a group? It's not complete. 4 or less participants. Just there. So you have 3 participants, right? And you have 3 people, so we still need a group here. Okay. You 3, after the presentation, come here, please, to talk to me after the lecture of professor. And the group of 3 people come to talk to me too. If your group has 4 participants, also please come to talk to me, and we're gonna solve. Or Amanda, who is in the back of the auditory, okay? That's all. Thank you very much. Enjoy the lecture.
Good. You can hear me on the back, right? So let's start the last session, the last lecture of the 3 ones I'm devoting to quantum links in superconducting quantum computers. Before that, let me clarify a little bit what I explained the other day. It had 2 parts. The first one ended with this experiment where we could see how if you provide energy to a qubit and you excite it, when the qubit relaxes, it produces a photon. And the experiments in superconducting circuits are so slow compared to other experiments that we can really resolve in time the spectrum of that photon. So what you see in this picture is simply a demonstration of quantum optics, how a quantum emitter generates a photon by decaying and producing a distribution of energy that, within the time of decay, concentrates in the resonance of the quantum emitter. This doesn't have to do anything with quantum state transfer, okay? On the other hand, I show you this other experiment by the group of Andreas Wallraff, where they did something related but not completely similar. The previous experiment was incoherent. We have a drive of a qubit. We move the qubit into a mixed state, half probability, 50% in the excited state, 50% in the ground state, and it creates a photon. This one is more sophisticated. We have a qubit coupled to a cavity. They talk together, and by the adiabatic passage, we can map the quantum state of the qubit onto the quantum state of a photon that eventually leaves the cavity. This second part is the one that is interesting for quantum state transfer. Okay? So the previous one was just ideas of quantum optics, and this second process where we can inject a photon deterministically, and that's the key, preserving the coherencies of the qubit that generates it is the basis for quantum state transfer. So let's move on to the idea, which is to make this full protocol where you're not only creating photons, you are also taking those photons through some communication channel. It can be a free space, it can be a waveguide, and you convince another quantum node to absorb perfectly that photon and recover the information. So to analyze this, we need to do a quantum optical model of such a device. The most general model that we can write for such a system is formally very simple, but very sophisticated. It consists of a spectrum of bosonic modes. These are going to be the propagating or standing waves that carry the information from one quantum node to the other. This can be, for instance, a waveguide. This can be a microwave cable, a coaxial cable. This can be many things. And these photons, they will couple to the qubits, in this case, through a simple dipole coupling. As we have seen when we were studying how a qubit couples to a cavity. So all the physics we saw before can be applied to this model. The difference is that instead of being just a cavity QED, this is called the spin boson model, because we have a collection of quantum emitters, which are two-level systems, spins, interacting with a bosonic bath in a process that we are going to make coherent. Normally, when you see this model in quantum optics, the first thing you try to do is to get rid of the bosons and find the master equation only for the emitters. So you trace out the coherent part that goes into the bath, because that's lost. You don't see it. The difference between that typical procedure in quantum optics is that we are not going to do that. We don't want that. We want that if some information leaks from one quantum node into the waveguide, it has to be recovered in some other quantum node. So we cannot get rid of the photons. We have to find a way to work with them that is easy and that allows us to move information from one side to the other. There are many approximations you can do to simplify your life. One of them is to assume a linear dispersion relation. We will lift this approximation later on. You can also take your couplings to be not too strong, lay, for instance, in the ohmic regime, where the interaction strength goes like the square root of the frequency of the photons. That's a very smooth, very gentle function, almost uniform, typically within the bandwidth of the photons we are going to create. And with that, you can do a lot of theoretical, apply your theoretical machinery from quantum optics. The first thing we are going to do is what you saw already that works very well in the cavities, which is to do a rotating wave approximation. So out of the product of the sigma x with, in this case, the electromagnetic field, only a few terms survive that describe the coherent exchange of excitations between the qubits and the photonic field. We eliminate processes that simultaneously excite the qubit and the field, because those are off-resonant, they don't conserve the energy, and for these small couplings that we're going to work with, they are not relevant. But immediately, the moment you do that, your life is tremendously simplified. You can get a master thesis project out of this, because this Hamiltonian has a conserved quantity. The total number of excitations that live in the qubits plus the total number of excitations that are photons is a quantity that is conserved by the Hamiltonian. It commutes with it. So this separates your subspace into blocks that can be analyzed individually. Naturally, the vacuum is not very interesting. If there is no excitations, nothing is going to happen. The next most interesting thing is when we have one photon. Okay? So that leads us to this very nice machinery, which is called the Wigner-Weisskopf ansatz, where we construct generic wave functions within these subspaces. For this talk, I will focus only on the single excitation subspace. Basically, you will have a set of complex numbers describing the probability that one qubit gets excited, another set of complex numbers describing the complex amplitudes that create a photon moving through the waveguide. This idea can be exported to more photons. In our group, we did a small code. It's available in GitHub, where you can put the number of bosons, the number of qubits, and the number of excitations, and you build the Hamiltonian. The problem with this approach is that, as you see here, the number of parameters grows very rapidly with the numbers of degrees of freedom, so we are not going to be able to do very sophisticated calculations. You will see simulations with up to 2 excitations in this final lecture. But already with this, you can play a lot. I have a notebook in GitHub in a folder called CQ, for C Quantum. These are examples of quantum optics programmed in Python. And there you can see this applied to study the spontaneous emission of a qubit into a waveguide. And you simply need to know the spectrum of bosons you are going to talk to, the energy of your qubit, and the distribution of couplings that you can deduce from the formulas I showed you before. And when you simulate this is a very sparse matrix that can be efficiently simulated with approximate exponentiation in Python. There are many tools. You can look at them, and this is extremely efficient. What do you get out of this? Well, you get the usual spontaneous emission profile with an exponent that is your decay rate. So all the information that you have here can be gives rise to this very simple dynamics. So this is very complex, but there must be a model that looks like this that describes the effective behavior of the qubit in the bath. No? This is what you have learned in quantum optics. You put a qubit in a waveguide, and it decays, and you can end up with a Markovian equation like this. Yes? Or I can also repeat the questions for the recording.
For that n equals 2 case where you have two excitations, so you can have a qubit excitation and the bosonic field excitation, or can you have, for example, no bosonic field excitation and two?
You can have one
So it's all
excitation on each
combinations.
qubit. You can have two traveling photons, or you can have an entangled
combination.
superposition of one qubit exciting and one traveling
Okay.
photon.
Yeah.
So that you realize that if you have n modes, you have two excitations. The Hilbert space is of the order of n squared. 3 excitations, n cubed, and so on. It grows exponentially, so not very manageable.
Thank you.
But what I wanted to say is that you have now two tools. One is exact simulation of your system, and the other one is the possibility to create effective theories that describe how the qubit behaves. Okay? In this particular case, it behaves very simply. Your complex amplitude follows an exponential curve, and it can be analytically predicted. We're going to see how it's done. But we want to do quantum links, so let's not put just one qubit. At least we need two on the sides of one cable. So if you do that, and you plug the variational ansatz into the Schrodinger equation, you get that the exact dynamics can be mapped into a couple ordinary differential equations for the amplitudes, the complex amplitudes of the qubits, and the complex amplitudes of the photons. Basically, you see here that the qubits and the photons oscillate. Here is missing a psi k. Oscillate with their natural frequencies, and the coupling makes them exchange amplitudes. So basically, the photons can feed the qubit, and the qubit can decay and feed the photonic field. Okay? There's a typo. Okay? Psi k is missing. The next thing to do is to try to find a way to work with this, similar to what we do normally in quantum optics. And the easiest thing is to integrate one of these equations exactly to insert it in the other one. Because there are more degrees of freedom in the photonic field than in the qubits, the right approach would be to first get rid of this one. And so you can get this formal solution for the photons, where you have this intuitively appealing expression. This would be the initial field in the waveguide, photons bouncing back along the cable. And then this would be the field that is deposited or subtracted by the interaction with the qubits. Okay? So that's those two components. Now, if you know what happens to the qubits, you know exactly what happens to the photons. That is going to be the basis of what is called input-output theory. Now we put this solution into the qubit equation, and you get three terms. First is the rotation of the qubit with its own intrinsic frequency. Second is the driving of the qubit by the electromagnetic field that was present initially in the waveguide. And third is this weird thing. It's an integral differential equation where you have the state of the qubit at different times in the past modulated by a memory function k. This is the first thing we have to do more carefully. This k is a Fourier transform that consists of lots of exponentials oscillating with all possible frequencies of the photonic field, modulated by the coupling of those modes to the qubit. So what does this function look like? It's not going to be very different from other derivations you have seen probably for master equations. We're simply doing it with more care. Because the first thing we have is that we don't have an infinite path. We have a cable. We have a finite length. So if a qubit deposits information, it's not fully lost. It can even go back to the qubit eventually. So if you put the conditions I showed you before, the linear dispersion relation with equi-space modes, what are given by multiples of the fundamental wavelength of this cable, what you find is that this memory function is periodic. And it's periodic with a time that is simply the return time of the photons. So if you have a cable of length L, there's going to be a time for a photon to go to the one side and return, which is simply the quotient between the length of the cable and the speed of light in that particular environment. So your memory function reproduces the physics that we expect from a non-Markovian environment. That's the first change from conventional quantum optics. The second change, well, it's not really a change. It's something that we have to be careful. we have lots of couplings to many modes. You saw it in the experimental picture of the generation of a photon. If you look at a very short period of time of how an atom deposits energy in the electromagnetic field, it tries to deposit it in all possible modes. Eventually, in longer times, those amplitudes will destructively interfere, and you end up with a narrow bandwidth packet. But you have, in principle, a broad set of couplings spreading the coupling of the qubit to all possible spectra. Your photons can appear anywhere at short times. That means that the memory function, which is the Fourier transform of the spectral function, has to be narrow, has to be very narrow. Okay? And the width of this function is usually called the memory time of the path. Okay? It's how fast your quantum system loses the information into the bosonic environment. And the third ingredient is that while number 2 is the usual thing you do in quantum optics, number 1 and number 2 combined tells you that your memory function is a train of peaks. So it's no longer just a delta-like function at time 0. You have recurrences of that function at multiples of the time for the photon to return. This changes a little bit the physics we are used to. But it's not too difficult to manage. What's going to happen is that the equations, instead of just giving you just a complex number, a decay rate, they have to be a little bit more involved. The qubit knows about its past. And one qubit on one side knows about the state of the qubit, the other qubit in the past. So and those correlations appear in the differential equations naturally. I've made this problem, which is very simple. If you put down this distribution of couplings, assume a linear dispersion relation of equispaced modes, you can compute this analytically. Essentially, you will get a train of diverging peaks with a finite height and a width that depends on this cutoff that we put here. This is the largest frequency that you allow in your experiment. Normally, it's something that we don't have access to. It's just a theoretician's tool. But this determines the memory time of your system. You can do it. It's a nice trick. It's a very useful model for making useful calculations in different contexts. Now, let's put this memory function in the equation I showed you before. What do we expect from the dynamics? If you solve the problem numerically, you kind of see this behavior at short time. So if the cable is infinite, your atom will decay exponentially, and this will be oscillations of this will be the imaginary part of or the real part of the amplitude of the qubit oscillating with a frequency that's the intrinsic frequency of the qubit. This is modulated by an envelope that is essentially the exponential that dictates the spontaneous emission of the photon. But if you look at the time scales, this happens in a time scale that is much longer than the memory time of the cable, of the path. So the information is lost very rapidly, much rapidly than the qubit has time to oscillate. This, well, for all purposes, if you look at the product of the qubit wave function with a memory function, the memory function doesn't really care about what's happening to the qubit. It doesn't see that change. So that allows us to make a very neat approximation where we take this integral differential equation, we replace it with a set of peaks. These are not necessarily delta functions, they're simply peaked functions. And we impose that this dynamics of the qubits is going to be, there's going to be a separation of time scales. There's going to be a slow envelope that describes the time scales for energy to be released into the photonic field. And there may be some faster oscillations associated to the phase of the amplitude that we cannot get rid of in the integral. Okay? But we have changed the problem significantly because now we can reconstruct from Wj C. So Wj is essentially a product of C times an exponential. So you have your unknown, the same unknown, the input field, the unknown again, and an integral that is finite. That depends on time, but you can do it, basically. So these things you can do. There's going to be multiple repetitions of the unknown. This is C j essentially at different times in the past, depending on what is this duration. There may be multiple peaks that are involved. But it's just a simple delay differential equation that involves the states of the qubit. You can do it yourself, convince how this looks like. But for the 2-qubit system that we have, we are going to truncate this series to include only these 3 terms. So one of the integrals, which happens between 0 and the half of the first peak, is going to give you a complex numbers that will change the frequency of the qubit and will include this relaxation rate. The same thing will happen for the other qubit around t equals 0. And we are going to keep another peak that describes how C2 is fed from the first qubit in the past. In principle, we should need to continue this series again and again until we have infinitely many peaks, depending on what is the time of the simulation we are doing. But we are going to impose a physical argument. My goal is to take the energy of this qubit, whatever it is, and transfer it to the second qubit. I don't want anything to go back. So I will design the dynamics so that these terms and other repetitions, they don't appear. Okay? So this is not an approximation. This is a kind of boundary condition for what I have to do with this equation. If what I do doesn't fulfill this condition, I'm breaking down this model. But physically, I'm going to use this part to describe how photons are emitted from the first qubit. And I'm going to use this second part to describe how photons are going to be absorbed, but never reflected back from the second qubit. Okay? So let's try to find out what do we do mathematically to ensure that this equation is correct. But before that, well, let's simulate what happens when you have something like this. Let's put simple numbers, gamma 1 equals to gamma 2. We put the same frequency of both qubits. So what do you expect that it will happen? Any guess? Louder. Cancellation. What does it mean physically? I'm talking about the physics. So if interference. What's happening? So one qubit decays, creates a photon, and what happens then? When the photon arrives to the second qubit, it will excite the second qubit. And then it decays and reflects back the photon. Okay. Is the qubit going to be completely excited or not? What's your guess? Yeah, but how tall does the qubit get? So does it fully go to the 1 state or in between? I'm going to give you the answer because the simulation is very easy. You can do it with Mathematica or Python. It looks like this, okay? So you have an exponential that decays, and this exponential photon with a very weird wavefront goes to the second qubit, and it cannot be fully. It's not well impedance matched. So the second qubit cannot passively just wait there and let the photon come and grab it. If you don't do anything, the photon is not completely exciting the qubit. You reach up to 60% probability of excitation. So what this tells us is that it's not enough to have gamma 1 and gamma 2 and this delay differential equation. We need some control. And this is something that, the scientists I mentioned before realized, and it's the basis for state transfer. But yeah. Yes.
In the large T limit, both curves go to 0. So what happened with the information in the qubits?
Well, eventually there will be a revival. And
Okay, they will eventually go up.
Goes back to the other one, and basically you have a photon bouncing back and forth between both qubits with a very weird dynamics. Okay? But if we allow time to go further, then we are violating the approximations I made before. Okay? Now, this probability is not really good. It's very small. Okay? Why is it very small? Because this is not fully quantum. Okay. If you want to think about this as a quantum channel, you need it to operate as a quantum channel. Yes.
Excuse me. You were making the discussion about like how the second qubit will not be fully excited by the photon.
Yes.
This is maybe I'm still with doubt about why is that the case? Is just like they have different energy gaps, or?
No, it's simply because this photon shape is not very good.
Oh, okay.
It's not designed to drive a qubit and excite it.
Okay.
It's the wrong wave packet. If you could flip back the wave packet, turn the shape, turn the tail the other way, then this gentle behavior might excite the qubit perfectly. But that means you have to invert time. You have to make the complex conjugation in time of this wave packet, and that's not really feasible. So we need to change this wave packet shape. But yeah, so the other thing I wanted to emphasize is that this transfer quality is really, really poor. If you think about all possible qubit states that you can transfer, and you compute the fidelity, it's below the threshold for this being quantum. Okay? If you have a classical approach and you measure the states of the qubits initially, maybe you can reconstruct this density matrix and copy it on the other side. This will be fully classical. And this gives you a fidelity, an average fidelity of state transfer of 2/3, which is above what we have achieved with this approach. Okay? Even if we stop the simulation at some point. So this is not very good. Another way to look at it, and which is a bit more rigorous than this traditional point of view of quantum optics that only looks at one qubit, is to think about how you can spread entanglement. This is a more canonical definition of fidelity. This is entanglement fidelity, where you have that you create a maximally entangled state on this node, and you send one of the photons in this mechanism to the other node. So one qubit stays here, the other one travels. So that means one qubit suffers the identity map, the other qubit is going to experience this bad state transfer protocol. And when you compare the fidelity of the perfect transfer of entanglement with this state, you will find that you get to the worst case scenario. The worst case scenario is 1 over the dimension of your space, which in case is 1 over 2. And the average fidelity that we showed before is related to this number and gives you 2/3. So we need to go above this number to make it a truly quantum channel. We need to change the way this is engineered. Any other questions so far? Okay, so let's do that. We're going to massage the equations to get more information about what is happening there. I showed you before that you can actually compute the wave packet, the dynamics of the photons, from the dynamics of the qubits and the initial state of the electromagnetic field. If we assume the waveguide was initially empty, all the field is generated by a qubit. There are mathematical relations that, in the dynamical equations I show you, connect the field that appears in the equation for the qubit, the driving field that drives the qubit, to the field that the qubit deposits in the waveguide. And those relations are called input-output relations. It would be if there is some photon wave packet coming here and it drives the qubit, the output wave packet is derived from the input wave packet plus the electromagnetic field created by the qubit, with some factors that depend on the spontaneous emission rate. This can be derived from the equations I showed you before, taking the limit of t plus and t minus in the dynamical equations of the photon. But that means that we know what is the shape of the photon that is going to be expelled, but also if we time reverse this equation, we would know what is the time, the wave packet that the qubit would like to absorb. There are both approaches. So let's keep in mind this first equation is, if I want to create a given photon shape and there is no electromagnetic field in the waveguide, the photon shape is determined by the dynamics of the qubit and how I control the coupling between the qubit and the waveguide, both numbers together. Okay? Then the second equation that is very relevant is what I said before. In the delay differential equations, or dynamical model, we are not going to allow any photon to be reflected back. So you can use the previous physical interpretation to realize that we want the output field of the second qubit to be absolutely 0. The output field of the second qubit is the interference between the field generated by that qubit and the input field, which is the field generated by the previous qubit. Okay? This is clear? So you have an input photon that's generated by one qubit, and this interferes with the electromagnetic field emitted by the second qubit. I've played a trick here. I mean, this would be C1t minus the delay going from here to here, but that simplifies a lot the equations and doesn't change at all the calculations. So this is it's called the darkest state condition. And what it says is that if you have found the shape for the first qubit's dynamics, that is the wave packet dynamics and the control to of the interaction with the environment, you have somehow determined what you have to do in the receiver node. Okay? So the dynamics of the first qubit determines the dynamics of the second qubit. And this is the problem. If you put here constant numbers and you put here an exponential, you get here divergences for the second qubit. So that means that what we saw before cannot satisfy this dark state condition. Then there is another equation that can be derived from both of them, but we have to handle it separately, which is that we want the conservation of probability. We want that all the probability that was initially in the first qubit is going to be transferred to the other qubit. That gives you something like this. So you have that all the dynamics of the two qubits, the combined probability, is simply the probability, the amplitude of probability that is in the reflective photon, which is 0. Okay? That tells you also that the state of the second qubit can be determined from the state of the first qubit, essentially. So we have now two equations. We have this relation with 1 and 2 unknowns that can be derived from this one, but we added the new equation that directly relates C2 squared with C1 squared. So that means we have solved the problem. If you give me essentially gamma 1 on time determines the dynamics of the first qubit. It determines C1 of t. Gamma 1 of t and C1 of t together with these two equations determine both gamma 2 of t and C2 of t. So you can design a control for creating a photon on one side of the waveguide, and I can tell you what is going to be the dynamics of both qubits and the control you have to put on the other side of the waveguide. Is this more or less clear? So this is exactly what happens. So you have this analytical formula for the control on the first qubit based on the wave packet that the first qubit is going to create. Essentially, W squared is the amplitude of probability that is going to be deposited into the waveguide. From gamma 1, via the previous equations, you get gamma 2. This is the control we have to apply on the other side of the waveguide to perfectly absorb the photon on the other side. And this tells you you have solved the problem. Now it's a matter of you telling me which photon wave packets you can and want to use in this state transfer experiment. Some traditional wave packets people have been used are hyperbolic seconds because they are exponentially decaying. They have exponentially decaying tails that mimic a little bit the exponential decay of a spontaneous emission. They are analytically very simple, and they give also an analytical formula for both controls. And the thing that you realize here is that hyperbolic seconds is a symmetric photon wave packet, and it makes the first control, the emission control, to be the time reverse of the absorption control. This is a general statement. If you engineer symmetrically, time reverse asymmetric wave packets, there is time reversal symmetry between the control for the generation and the control for the absorption of the photon. Basically, what happens on the first node is the time reverse process of what happens on the second node, essentially. This symmetry was recognized by those gentlemen, Chirac, Mabuchi, Kimball, and Soler, and this is how they imposed that they wanted to design, or they had to be designed, these wave packets. Now we know that this is not true. Whatever wave packet that doesn't give you weird things here that cannot be experimentally done will be a suitable state transfer protocol. Everything that you do that makes this not divergent is going to be OK. But in general, if you plug something like this in the previous formula, if you plug a wave packet that has this property, what you can realize is that this integral is 1 minus this integral. So essentially, they are going to give you the same quotient, and it's going to give you the same control. It's going to give you exactly this. But as I said, this is no longer the case. And in practice, in experiments, you cannot really do this. There's going to be some asymmetries between both sides of the experiment, and we have to engineer the separate controls for the emission and the absorption. OK, so far, this was a completely idealized view of how a quantum leak is designed from the point of view of quantum optics engineering, with just 2 qubits and a cable that connects them. Now I'm going to tell you the work we have been doing in the last years around slightly more sophisticated setups and how you have to improve a little bit the models I show you. Our work begins with this picture. It was a 5-meter quantum link between 2 small quantum processors hosted in 2 fridges here. This experiment was created in the group of Andreas Wallraff as a prototype towards more ambitious experiments that we will explain later on for testing Bell inequalities. But basically, it was the excuse to ask for a project that allows us to scale these setups to larger sizes and to better understand the theory of state transfer in these very large connections. Just to give you a scale of what was achieved at the end of the project, there is this nice video you can find in YouTube. Come on. It's a handheld camera. It shows the size of the experiment at the end. You start in one refrigerator, which hosts 1 superconducting chips. And then you go all the way through the cellars of ETH, Zurich, to the other side, 30 meters, with an intermediate refrigerator to keep the Wi-Fi cool until you reach another processor hosted in that other fridge at the end. It's a quite impressive achievement. It's more than 1 ton of isolation, plus the weight of different devices, compressors, and things like that. Probably a few thousand screws to manage, but I don't want to think about that. Very nice setup. OK, so that's how the video looks like. That's a little bit of engineering view. You have 3 fridges to keep the whole setup at cryogenic temperatures. And everything is going to be with these 3-dimensional waveguides we saw yesterday. This is not cables. Okay? So this is going to be really, I think it's aluminum tubes going all the way from one side to the other, operating at millikelvin temperatures, and transporting microwaves from one side to the other. So it looks like this. So you have an experiment with a few resonators hosting qubits, like here. And those qubits are connected to the waveguide only through resonators, through LC resonators in a chip that then go to an impedance match element that couples to this tube. And at the end of the tube, they have another coupling to another resonator and to the qubit. So quantum optically, it looks more or less like this. 1 or more cavities acting as filters between the connection of the qubit and the waveguide. There are 2 purposes for these resonators. One is that they act as filters. So they have a narrow bandwidth around 1 frequency. If you move the frequency of the qubit outside that bandwidth, the qubit is more or less protected. And the other purpose is that, similar to what I showed before, if you put the qubit in contact with the cavity, you can engineer a coupling that allows those excitations from the qubit to go into the cavity coherently and then into the waveguide. So we can control the tuning between the qubit and the cavity formally. So that changes a little bit the quantum optics approach, but essentially it's just we have this recipe of things we have to achieve. First, we need to inject photons in the waveguide. We need to shape those photons. We need to transfer the quantum states by combining both things. And we need to show that you can create entanglement in this device for quantum computing applications. And I'm going to basically describe a couple of papers that were done in collaboration with Ricardo Puebla, former postdoc in our group and now tenure professor in Carlos III, and Guillermo Peñas, a PhD student that was overseeing this project. He was doing all the calculations and the models. The first part is just a cautionary tale. I showed you before that we have a numerical approach to modeling the whole system in the single excitation limit. That is required to get a little bit of a better understanding of effects like putting more than one resonators in these experiments that change the equations, understand the approximations, and so on. And one thing that you realize as a theoretician is that the moment that you connect one quantum object to another quantum object, your quantum object is changed. And the models I wrote before, they didn't take that into account very well. Okay? So we have the frequency of the qubit. Well, what happens in this case is that when you put your cavity in contact with this waveguide, the effective frequency of the cavity is shifted. And this shift doesn't look like a lot. It's up to 0.1 megahertz in our calculations. But if that shift is not properly tuned, we will not be able to engineer perfect state transfer. So this is simply a thing that if you are a theoretician, be careful with your quantum optical approximations. You cannot get rid of lamp shifts. If you want to do things that are useful for experiments, you have to do it with a little bit more care. But the first part is more or less clear. No? We have either direct connections before, or in this case, mediated by a cavity. We are going to do the same thing. So this is a theory of cascaded systems. Basically, one system gets probability from the other, and this system gets probability from the other. And these are cascaded equations that we can solve semi-analytically and get recipes for the photon wave packets. So this photon shaping, it can be achieved. This is a numerical description of what we have to do. We are going to create symmetric wave packets. And these are going to be the controls we compute numerically. And you see that they are no longer necessarily as same as before. In particular, we have to change the calculations because now we have not the qubit coupled to the waveguide, one simple input-output theory. You have a qubit coupled to a cavity, which is coupled to a waveguide through this decay rate. And you can still do input-output, find out the wave packets of the outgoing photons. But now the wave packets depend on the state of the cavity, which itself depends on the state of the qubit. Here there is some A missing that should be here. Sorry, it should be here, A. But it's again an inverse problem that can be solved for as many cavities as you want to put in the middle. You can compute the probability of the qubit. And all the probability that leaves the qubit is attributed to the wave packets that are going into the waveguide. And you can find out the control. And not only that, one thing I didn't explain before, you can not only control the amplitude of the wave packets, you can control the shape, the instantaneous phases of those wave packets by changing the phases of the coupling between the qubit and the cavity. And that's crucial in practical applications. Another thing that I didn't say before, but is also very relevant, is that you cannot create any photon. Either the qubit or the cavity they have a maximum speed at which they can deposit energy into the environment. That means they have like kind of a filter function. That's around the resonance, you have a bandwidth, given by the maximum spontaneous emission rate, or in this case, the decay rate of the cavity. So you can only create photons that, first of all, the logarithmic derivative of the amplitude has to be bounded. That means that they must, at most, decay like an exponential. They cannot be faster than that. It cannot be Gaussian, for instance. And then this logarithmic derivative is related to a physical property, like in this case, the cavity bandwidth. And that sets a speed at which you can create those photons. What you can do is that you can do slower things. So you can have a cavity with a bandwidth and create photons that are narrower than that by simply changing the control to have narrower wave packets. And that's part of our photon shaping protocol. In experiments, they actually reach up to 2 filters to even lower the probability that the qubit that is detuned decays into the cavity to protect better the qubit. As I said, you can do these calculations. They are in our papers. We are not going to discuss them. So this is what happens. We didn't discuss it before. You start with a qubit excited. The qubit, we connect the coupling with this profile. Begins to deposit energy into the cavity. And you see here the probability amplitude of the cavity. And this cavity decays into the waveguide, depositing energy into the waveguide, which is then reaching the second qubit. It's mapped into the cavity and absorbed by the second qubit. And this process has almost 100% fidelity. The shapes of the wave packets are the shapes of the controls in the particular scenario, and hyperbolic seconds with the right tails that we want to have. If you want, because we are doing exact simulations of these models, you can reconstruct the photons in position space. It looks more or less like this. You create a photon. The photon goes to the second qubit. If you don't do anything, it's going to bounce back and forth. What we are going to do is we're going to absorb it perfectly, and nothing is going to bounce back. Another detail that we have to control as a theoretician is the fact that these tubes, these waveguides, WR90 microwave waveguides, they don't have a linear dispersion relation. They have a gap. They have a parabolic dispersion relation. And you see this here in the fact that the photon that you initially create, every time it bounces or every time it goes to the waveguide, it gets broader and broader and broader and broader. That's simply the dispersion of the photon due to this parabolic dispersion relation. That's something that is going to affect the quality of your transfer. We can do another thing is you can change the length of the photons. You can make them slower to a point that you cannot really distinguish the process of emission from the process of absorption. Both things happen simultaneously. It's interesting because in a way, this violates the usual approach to input-output theory where you have one process that creates something. You get the output of that process and forget about the system, consider its propagation, interact with the second system, and this gets absorbed. This limit, in principle, it should not be describable with the models we have done so far in traditional quantum optics. But because we have done this careful study of the memory functions, these periodicities, and so on, we have a rigorous understanding that this is correct. And this is going to be very relevant because at this point, the photons are so long and they are so narrow in frequency that they can see the individual modes of your waveguide. So your waveguide has a finite length. It has a lot of modes spaced by small frequencies. And the photon can really resolve that spacing between the photons. And so we have this kind of two limits of state transfer in this particular device. We have the limit of short photons that are created very rapidly. They are shorter than the whole cable. We see this tendency of the infidelity that gets worse and worse as we make the photons shorter and shorter. And on the other hand, when we make the photons longer, we can get extremely good fidelities of state transfer that almost improve exponentially, but there is a saturation around here that we have to explain. The first thing we can understand fully is this part here. This is simply dispersion. This is the fact that we don't have a linear dispersion relation, and the photon that is emitted here, when it reaches this second point, is distorted. So your memory function is not just a delta peak. It has some structure that diffracts the little bit the wave packet. We are going to operate this, and we can improve that. In principle, you can improve it by making the photons narrower. This is what happens here. The other thing is that there is this limit in which we have very, very long photons that can distinguish the different This will be, I don't know, omega k plus 1, omega k plus 2. And we are putting the qubits around here. And the photons we create, maybe they have a bandwidth like this. Maybe they involve a couple of modes at most. It would be very tempting to use a cavity model to replace these dynamics. But if you do that, this would be these curves on the top. Your dynamics of the cavity has to be extremely slow. It's a very precise, very inaccurate model. Andrew Cleland improved on this by taking, we will see the experiment, one qubit, one mode, another qubit, and doing stirrup. Those are these curves you can see here, these curves here. But the best thing we can do, and the fastest thing and the highest fidelity, is simply just putting these controls we have designed with input-output theory, which, as I said, is very weird to assume that we can do the theory we did when your system has an almost discrete spectrum, and propagation is an alien concept to the actual dynamics. OK. Going a bit slower. Next thing is that we corrected the dispersion in our works. The idea is that dispersion is simply affecting the phases that the wave packet sees in Fourier space. And those phases are not linearly growing. They are quadratically growing because there is a parabola. What's the solution to that? Well, try to make a photon that is not going to be distorted. So you engineer a photon that you emit so that when it travels through the waveguide, it has the right shape when it reaches the second qubit. Another alternative is you engineer a photon, learn the distortion, and change the second control to absorb perfectly that photon. Both approaches are OK. And in fact, when you have a very long waveguide where the distortion can be pretty large, you have to do both. You have to engineer both sides of the experiment to improve it. So you have to imprint phase controls on both sides of the experiment. And this is what you can see, for instance, for one of the simulations. This would be the infidelity of the state transfer protocol as a function of the bandwidth of the photon, or the decay rate of the cavity. If we make this correction, we can go down here. Why can't we go down further down? Well, the reason we cannot go further down is that one thing we are doing is we are changing in time the coupling between the qubit and the bath. And that's a very aggressive thing to do. Normally, I showed you before, we assume that the dynamics of the qubit is going to be very gentle compared to the memory function. If you begin to chirp the coupling, you need to improve your theory and go beyond Markov. The integrals we did before have to be improved. And actually, you have to do iterative improvements on the equations that give you corrections. This will be the first order correction that you would get in the integral if you assume that the envelope is not too slow. And that you can even further improve, go down and down. But the cost of that increases quite dramatically for the theoretician. It's really not worth it. OK, so skip that. Then let's talk about how you would would you use it in a quantum computer. One possibility would be simply to shuffle qubits back and forth. Basically, we have discussed it before. If you have one quantum state for the qubit, this is going to be mapped to a superposition state of vacuum and one photon with a particular shape that we have engineered. And then when we do perfect state transfer, this is going to be mapped again into, ideally, the same qubit on the other node. If you do that, as we discussed before, you may end up with different quantum computers where this moving of qubits is one more part of your toolbox. So you can virtualize a set of coupled computers as it was only one. You can even do a little bit more sophisticated things, which is try to do gates. The simplest way to do gates would be to do this kind of thing. So you start with a qubit. You send the qubit to the other computer. You do a 2-qubit gate here, and then you move the qubit back. And this is like having a distributed gate happening between both quantum nodes. It's a trivial generalization of this idea of swapping qubits. Just going to briefly mention that there are other things that you can do that have been demonstrated in the lab recently. For instance, you can do passive gates. The previous problem is that you have to do perfect state transfer, synchronize everything. It's a bit messy. One thing you can do is you can transform the qubit into a flying photon, let the qubit go against the next quantum computer, and instead of engineering the perfect absorption of this qubit, you put this qubit slightly off resonance from the cavities. What happens is that the photon that comes in is going to do a measurement, so to say, of the qubit. It's going to be reflected with a phase that can have one sign or the other, depending on the state of the qubit. This has been demonstrated repeatedly in many contexts, including optical experiments, but also in superconducting circuits, also a group of Nakamura. This is called collisional phase gate. And, well, it can be done in our experiment. We have simulated how it works with these same protocols that we just discussed. You only need to control the photon generation at one side, let the photon emit, and then control the absorption at the same place where the photon was originally created. We can do it because this is a non-Markovian system, and this creates a simple phase shift. There are design compromises on this. This gate is not too fast, but it can be done. I'm going to skip the details. You can see it in the papers. And then the last ingredients that we need to put into this is scalability. This is the last thing we have been studying, is how to send more than one qubit. The things we have discussed is just one excitation going back and forth, because that is the easiest theoretical thing we can study. Can we increase the capacity of this channel to put more qubits? There are different ways to do that. One way is simply to send qubits one after another. Let's do kind of scheduling of your information. The first option is called time-bin encoding. The second option would be to use different types of photons. And photons can be differentiated either because they have a different wave packet, they have different modes, would be this possibility, or because they have different frequencies. They are far apart in the spectrum. Both possibilities are feasible. We have done a study of this with the goal of understanding what is the capacity of these waveguides to transport information between quantum nodes. One application is quantum computer. We can increase the bandwidth. But there is another more important application, which is error correction. If you can only send individual photons, those photons can be distorted or they can be lost. Photons are very coherent in superconductors, but they can be lost. To improve the quality of information you transfer, you're going to need more qubits. If you can simultaneously send all those qubits in some correlated state and then recover it in the other side and decode the information, that would be extremely useful. So we would like to enhance the capacity of the cable by exploring how to do that. We tried initially with this mode multiplexing because it was the easiest thing that we could do. We have seen how we can control the shape of the photons we create and absorb by simply changing the coupling of the qubits to the bosonic environment. That's a trivial approach. You can go from perfectly symmetric waveforms like the hyperbolic secant to anti-symmetric waveforms, and you create a ladder of orthogonal modes for the state transfer. This simply changes the couplings in ways we can compute, and they are predictable. There are two problems there. One problem is that if the modes are close in frequency, when you try to inject the photons, the two qubits are going to disturb each other. That's one thing we found, so it doesn't work very well. The other problem is that in this approach, you want to reject the photons that are not in your particular mode. But whenever you reject a photon because it's reflected back from the qubit, will be this process here. The photon that you reflect back is distorted. because it interacts with the qubit. It's not that nothing happens to it. So this mode multiplexing didn't work very well. But we can do frequency multiplexing, which is the other option. We simply put the cavities, two cavities connected to the same cable, but let them have different frequencies. And here, it happens more or less what you would expect. The quality of the transfer depends on how distinguishable the photons that you create are. If the photons have a fixed shape, like a hyperbolic secant, but they are shifted in frequency, you can compute their overlap. And this overlap is going to be proportional to the infidelity of the state transfer. Why? Because when both photons arrive at the second nodes, the nodes where they have to be absorbed will not be able to tell which photon they have to take. If you make the frequency separation between the photons larger than the bandwidth of the photons, you get an exponential enhancement of the fidelity, and you go back to the fidelity of state transfer of individual photons. This plot here, it has been done with the Wigner-Weisskopf model with 2 photons. So this is a rigorous simulation of the state transfer of 2 photons. Unfortunately, we didn't have neither time nor the resources to do more than 2 photons. What can you do in that scenario? Well, the thing we came up with to estimate the capacity of this multiplexing was to take this as the worst thing that can happen between 2 photons, that they are not distinguishable, and use this quantity to bound the errors of sending multiple photons. So you do that with this kind of pessimistic estimate. It's simply all the errors that you could attribute to not being to distinguish pairs of photons. It's a product of errors, pairwise errors between all possible pairs of photons you are going to send. This gives you exponentially worsening curves, but they are not too bad. You can see that up to 100 emitters, you can get fidelities of 10 to the minus 3, 10 to the minus 4 in collective state. It's not for each photon individually. So that seems doable. In practice, we have to be careful because the more photons you put, the more frequency you need. And there may be devices like the waveguide we have seen that can have sources of errors due to distortion or other possibilities. So this was a more realistic simulation for different lengths of waveguides. And up to 60 emitters with 5-meter waveguide seems doable. For a 30-meter waveguide from ETH Zurich, maybe 10 would be stretching it. And we cannot do much more. But you can see that we can do a lot of analysis of these things with just this simple quantum optics that we have discussed. That covers all the theory that I wanted to see. Part of it is in the books I mentioned or the papers I have referenced. And as yesterday, you will get a copy of the presentation. Let me just summarize a little bit the experiments that are confirming that this is useful and doable. So this is the end of my lecture. And this includes some early demonstrations of quantum links in different platforms, not just superconductors. So this was the original proposal. And if you look at it, you see here a 3-level atom inside a cavity with a waveguide connection to another cavity with another atom. And indeed, at this time, most of the quantum technologies and quantum communication proposals, they were very much AMO-oriented. So you have atoms as protagonists of the designs. Particularly, this is a type of 3-level atom where you would drive this transition with an external field, and then this E state would get excited and decay, producing one photon, similar to what we have seen before. This is the original proposal, Bastirac, Soler, Kimball, and Mabuchi. And this has been realized in the lab, essentially. It's not an easy experiment. This was a very long, research program in the group of Gerhard Rempe, where first they had to find a way to put the atom in a cavity, in a very small cavity, where the atom is basically talking to the mode that is trapped between those two mirrors. That led to a research on conveyor belts, taking individual atoms and putting them on the cavity. There was research on creating well-shaped atoms, individual atoms from these cavities into a waveguide That was also research done by one of the organizers. And then the last part is to match both the emission and the absorption at a different node. And I don't remember the distances here, but 21 meters is pretty decent. The experiment in 2012, when I was in Max Planck at 2002, 2003, they were doing the conveyor belt, just putting the atoms inside the cavities and first photons. So it took a long time because this is a very difficult experiment. So the quality of transfer is quite good for the time. And you can see it analyzed in this density matrix or analysis of the process of state transfer between the two nodes. You see that the scheme is very similar to what those theoreticians were envisioning. You have a ground state encoding the information and different detuned transitions enabling the generation of photons, which in this case, both states create photons, but they are selected by the polarization. One state of the qubit will create one polarization, the other one, the other polarization, and that way you get always information from one side to the other. What's the problem of this approach is that here there is only one atom. But we want this to be one qubit out of a bigger system. So if you go with colatoms, this should be some kind of optical lattice, and there should be one atom in a particular optical lattice. That's a very challenging experiment. There are two alternatives that people have researched. One is to use trapped ions. Because trapped ions, they are trapped by electrodes. The atoms are charged, so they repel each other. They're very well separated. And from the early days where people studied how to trap these ions even in chips, they were investigating how to put fibers and couple light in and out of individual photons. This is a very beautiful experiment from Innsbruck, where they could interface up to 10 qubits from an ion trap, inserting one qubit after another and creating different photons, one after each qubit. It's like a selectively extracted information from each of the qubits in the trap. In this case, it was only measured. And recently, they have done better experiments towards quantum networks in this scenario. I've chosen to show you what we do, which is more like if we already have quantum computers that are very scalable and can be cabled, let's do that with that. And there have been a series of experiments towards that. The first one people typically cite is this one from 2018, the group of Yale, where what they have is they have a photonic field in one cavity, and they use a parametric amplification process to extract that continuous variable field into the waveguide. So this is not exactly qubits, as we have discussed them, but it's quite similar. Then there is an experiment by Deboré with a more complicated level scheme with a transmon in a cavity that is emitting a photon which is absorbed by another transmon in another 3D cavity, which is closer to what we have discussed. But there is this very beautiful experiment by Andrew Cleland, which cheats a little bit because all experiments I've said, including this one, they are in the same fridge. It's not between different processors. This one has a 78 centimeter waveguide printed in the chip. You can see it here. And it's nice because it explores two limits. One limit in which you make the photons so narrow that they can see the individual resonances of the cavities. So you can see, you can put the photon at a given frequency, and it can oscillate with the mode, the standing wave mode in this cable at this particular frequency. So they can do state transfer in the both regimes I showed you before. One would be where you simply assume that this is like a cavity, and after a very long time, a photon that is in one qubit goes into a cavity and goes into the other qubit. And that's a slow process, but they could also do not only a mode resolve swap, but they could also do, for instance, one qubit sends a photon, comes back and interacts with the qubit, and you see this ping pong of one photon exciting repeatedly the same qubit, or one photon creating one qubit and then perfectly absorbed in the second qubit. And there you see here the probability of transfer of the second qubit. So this is a nice experiment. It demonstrates all the principles of the quantum optics we have discussed. It's worth reading it. It's 2019. There have been more recent single fridge experiments that are equally impressive. There is this experiment in China where they connected 5 qubits with these cables. It's a little bit the philosophy of having multiple quantum processors connected in the same fridge and really on the same cooling path. And it was successful, and they showed a swap between different quantum processors. Well, this is more than 5 qubits, small quantum processors. And then there was this 64-meter coaxial cable connecting the two processors in the same qubit, in the same fridge. Well, these are still single-mode experiments. These are like cavity QED experiments in that sense. I'm going to describe you briefly the experiment we have been collaborating with, which is the one in Zurich. What I show you that we have two fridges connected by a huge tube, which has, as you see here, 1, 2, 3, 4, 5, 6 consecutive tubes providing isolation. The inner tube here, it can be at a very low temperature, close to 20 millikelvin, which is impressive given the size of the experiment. And then you have different tubes that are progressively isolating and at higher temperatures until you reach the room temperature of the environment. They have done many experiments with this setup, including state transfer experiments. This will be simply transferring a qubit and looking at the quality of the, looking at the quantum process and the quality of this quantum process. The quantum process that is involved in generating one photon and absorbing it at the other end of the network is very close to the identity with some errors. The error budgets are very well understood. This experiment is very challenging. There are many things that have to be controlled. The resonators on the one side and the other, they don't have exactly the same frequency. Then you have a coupling of a chip to a macroscopic tube with a device that is called an impedance match connector. As also a source of possible reflections and photon losses. So everything is known, but it's still an engineering challenge to improve this device. And despite this, this is still above what we required for a quantum description of the state transfer. So the fidelity is above 2/3. This is a quantum experiment, and one can think about doing really quantum correlation experiments with them and show entanglement distribution and things like that. And this is what they did. So the reason why this 30 meters and not the 5 meters I showed you at the beginning before we did the project is that we need this length. They wanted to do a belt test experiment. That involves creating entanglement between two quantum nodes and doing random measurements and finding out whether the correlations between those measurements, they can be or cannot be explained by a classical theory. And for that, you need things that are very far apart. Because what you want to do is you want to first create the entanglement between the two nodes. And then you need to select the basis in which you want to measure, to prepare the measurement, to implement the measurement itself, and get the outcome. And this has to happen much faster than what it would take any information to go from one node to the other at the speed of light. If you can do things faster than that, and you can demonstrate that you achieve quantum correlations, then that means that this cannot be explained by a local realism theory. That means we have shown the non-local nature of this entanglement. And so this is very challenging. That means that the time of the measurement has to be much shorter than the separation between both nodes divided by the speed of light. And that's, I think in this case, the separation is about 100 nanoseconds delay. And that's pretty fast. So you need to synchronize perfectly both experiments. Synchronizing things that are 30 meters apart when the signals that synchronize them travel at the speed of light is a very challenging task. And it's a very nice masterpiece of work showing the potential and the capacities of this experiment. And what you can see in that publication that's already 1 year old is that indeed they find that for certain separate measurements, random measurements, A and B basis done on both nodes, you can get a correlation that is above what can be explained by classical theories or local realism, hidden variable models. So this is a huge milestone, I think, in the development of quantum links for superconducting quantum computers. There are many improvements to be done, having more nodes, multiplexing, and in general, this opens many possibilities. So on the one hand, yes, there is the idea of having networks of quantum computers or connecting processors to increase the capacity. More generally, your processors will have to be connected to things. Eventually, sensors, memories, many algorithms that require quantum memories in different forms. But also from the point of view of fundamental science, we have a device that describes interacting objects whose interactions are now subject to causal cones that can be experimentally probed. So we have really non-local quantum systems. That we have many of them. We can explore a regime we call non-local quantum many-body physics. It's like interacting many-body systems with interactions that are no longer instantaneous. They are delayed. And that where the delay of those interactions can compete with the intrinsic timescales of those quantum objects and the controls we make on them. And that can give rise to very nice and interesting new phenomena that we want to explore in the near future. And of course, there is always error correction. There is always the quantum applications. There is always the question of how we can use these quantum links more coherently, and that's in a more algorithmic point of view, where many of you can also contribute in the future. And so maybe we can, at some point, reach this vision that ChatGPT has of a quantum network. It tends to put a lot of rays whenever I ask for these things. I don't know why these rays are quantum. Who knows? But yeah, this covers more or less what I wanted to tell you during these 3 days. Time for questions. Yes. You can give it to me. It follows? No.
A very nice talk. In the readout process of many qubits, and in the picture of using frequency multiplexing, are you generating a signal from the FPGA at lower frequency, or is at high frequency?
That's still theory. So we are still not, we don't still have a demonstration of multiplexing in these devices. Everything I've shown you is single photons, both in the atomic regime and also in the superconducting regime. We have seen time beam multiplexing.
Yeah.
Experiments where the emitter is used again and again to produce more qubits that fly through the waveguide and are used one after another. One thing that is true is that all these experiments with superconducting circuits now evolve towards very high-speed electronics.
Yes.
Already at the experiment I showed you before, or the Bell test, you have to synchronize 2 measurement apparatuses that have to work in times of nanoseconds, creating the microwave pulses that control the qubit for the measurement, getting the measurement out, extracting the phase of the pulse, and then doing the correlations. Plus interacting with quantum random number generators to choose in an uncorrelated way the choices of measurements. So those are very challenging experiments that require very sophisticated high-speed electronics, yes.
And the last one, to synchronize the both qubits, you are using one local oscillator, for example?
That I don't know. I cannot tell you how they designed the microwave behind it. I'm a theoretician. But you can talk to them. They're very nice people, so they can give you details.
Thanks.
Any further question? Okay.
So for those single transmission of a qubit state, what are current state-of-the-art fidelities, and how much do you think those can be pushed in the next few years?
Depends on the platform. I think that you can see here the optical experiments. They were close to the identity, 76%. Now this has improved a lot. There is this published paper, well, unpublished paper by China in 64 meters, where they claim 96% fidelity, I think, in 64-meter cable. It's not published, so we cannot verify whether it's fully correct or not. There is one, you can see it's above 70, so it's good, but they still have to improve the quality. And in the other platforms where they use cables, they can also do higher fidelities at shorter distances. So this is still not 99. It's not scalable yet, but there are engineering challenges that can be solved.
Any other questions? No. Let's thank Professor Juan again.